Hello. Yeah, let's get started. In this talk, I will show you how to provide security support for RDMA systems in programmable networks. Consider a scenario where a local application is trying to read some data in remote memory. Traditional protocols like TCP/IP involve the remote CPU to process the requests. So this will incur actual latency and consume more CPU cycles. Remote direct memory access, or shortly RDMA, enable the local application to read the remote data or write the remote data without CPU involvement. The magic happens in the RDMA-enabled NIC, or RNIC, which process the RDMA request and use DMA to operate the application memory with CPU bypassing. The proposal of RockV2 enable RDMA to run over converged Ethernet, and because of the high performance and easy deployment, many cloud providers today have widely deployed RDMA in their data centers. But RDMA was initially designed for private usage with minimal security support. But as it is increasingly deployed in multi-tenant public clouds, RDMA security has been a concern. Recent studies have revealed a lot of vulnerabilities in current RDMA systems, including illegal memory access, denial of services, side channel attacks, and many others. These vulnerabilities are caused by the insufficient RDMA-native security support. RDMA is unencrypted. Instead, it uses very simple credentials like QPN, RK, PSN. You don't need to worry about the details of how these credentials work. The key idea here is that these security mechanisms are not secure enough, and they can be bypassed by the attacker easily. First, QPN and RK, they are not randomly generated. Recent studies have shown that the generation of QPN and RK has a very predictable pattern. So this figure shows the RK value generated by 3 different RNICs. And as you can see here, the RK values for different memory regions are just increased linearly. Packet sequence number will be increased by 1 for every RDMA packet, but many RDMA applications use a fixed initial value, which makes it easier for attacker to guess the right value for packet injection attacks. And given that PSN and QPN, they're only 24-bit long, so it's possible for attacker to guess the right value by enumerating all possibilities. So in summary, RDMA-native security support is not enough. Attacker can bypass this mechanism to attack RDMA systems. Here is an example. In this example, we have a victim client and a malicious client. They're running on different machines. And they have created RDMA connections with the same remote RDMA server. And in normal cases, an RDMA client can only access a memory owned by itself. But an attacker can access the memory owned by the victim if she successfully guesses the right value for the credentials using the vulnerability I showed you on last page. Although the attack is not very complicated, addressing the underlying security issues in the RDMA system is very challenging. There are 2 possible solutions on the end host. First, we can redesign the RDMA protocol or the RNIC hardware from scratch. But the new protocol and the new hardware, they're not available yet, and it will take a long time for them to come out. But even if they're ready in the future, it still requires intrusive changes of existing RDMA systems to deploy them. We can also use a software approach. For example, we can deploy software security patches on remote CPUs, but this will negate the benefits of CPU bypassing. To address this problem in this work, we proposed a Bedrock. Bedrock takes a very different approach. It keeps the end host untouched and provides security support in the network. Bedrock is a platform with several security services. So far, we have provided source authentication, access control, monitoring, and logging. And it's not difficult to add more security services following the same approach we proposed in this work. Besides, Bedrock preserves CPU bypassing on the end host, and it can be deployed immediately in today's data centers. The key enabler of Bedrock is that today's networks have become programmable. Programmable switches are commercially available now, and they can be programmed with high-level languages like P4. P4 provides a program parser for us to extract RDMA header files, which can be further used as a match keys in match action tables to customize the processing logic on the switch. And here's a quick example. This table generates a log for RDMA requests with a certain queue pair numbers, memory addresses, and operation code. P4 also offers registers for stateful processing. For example, we can use them to measure the traffic rate sent by a certain RDMA client to detect the DDoS attacks. This programmability does not sacrifice the performance of the switch. The switch can still run at the line speed. Because of these benefits, programmable switches have been widely used to build security defenses for traditional protocols. And in this work, we'll use it to provide security support for RDMA systems. Next, my colleague Kuo-Feng will introduce more implementation details and evaluation results.
Thank you, Jiarong. So let me start with source authentication. I will use the same example Jiarong mentioned earlier, but here I also show the programmable switch and the ports it's used to connect to the clients. In this scenario, the attacker needs to spoof the victim's source IP, QPN, and other request metadata. Our key idea to defend against this attack is to utilize the invariance from network infrastructure that is beyond the attacker's control. This is possible because we assume a cloud setup where a network is trusted. Therefore, even if the attacker can spoof the IP address, she cannot control which port the packets will be received. With programmable switch, we can further create a mapping table matching on these invariants, including source IP and incoming port. Every RDMA request passing by, therefore, must hit an entry on this table. If not, they will be dropped. This technique can work very well if the attacker is on a different machine. But when the attacker is on the same machine as the victim, their packet will share the same incoming port on the switch. So we need to further obtain other invariants from queue-pair initialization using an eBPF module. You can find more detail in the paper on this. Another important feature of Bedrock is access control. This figure here shows an access control rule which specifies the start address and the address of an accessible memory range. It also specifies the permitted operation for that range, in this case, read-only. If a request has wrong range or the wrong operation, we should reject this request. To enforce such rule, we need to determine the containing relationship of the two ranges. One is from the request, and the other is specified by the RDMA application. In other words, we need to ensure the start address and the end address of the request are inside the range of the access control rule. We implement this mechanism using P4 language as a table like this. As you can see, we use range matching on the two address field of the request. An important challenge of access control is hardware limit. For example, a switch can only do range matching with a certain number of bits per field, for example, 20 bits. But an address field has 48 bits, so we need to partition this field into 3 smaller segments, each with 16 bits. Another hardware limit is that range matching consumes too much switch resource. So we further derive 3 rule compression techniques that can further optimize the usage of switch resource. Finally, Bedrock also supports monitoring and logging. With programmability on data paths, Bedrock can provide visibility to RDMA request processing, even when the server CPU is bypassed. You can find more details in the paper. Next, let's see how Bedrock performs. We set up a testbed with Mellanox NICs and a Terminal switch. In this testbed, we run 9 different attacks, which can happen in traditional RDMA systems. But here, with Bedrock, we can mitigate all of them. To further maximize the security benefits of Bedrock, we also have several optimization techniques to increase the number of access control rules. We evaluate Bedrock with and without these techniques on several workloads, and here is the result. As you can see, Bedrock can achieve up to 7 times more access control rules after the optimizations. In the paper, we also have several evaluations on Bedrock's performance and overhead. You can find more detail in the paper. In conclusion, motivated by recent discoveries on RDMA vulnerabilities, we took the opportunity of programmable switches to propose an in-network RDMA security suite, which can support 4 effective security primitives and is deployable immediately and extensible against future attacks. Our evaluation shows that Bedrock can mitigate up to 9 RDMA attacks with minimal overhead. With this, I conclude this talk. Thank you, and we are happy to take any questions.